and all. This is J. Anusha, working as lecturer in physics under the Department General Section. Working in SS Government Polytechnic, Zahirabad. And for first year, second sem students, the subject what I'm dealing with is applied physics with the subject code 18 common 203F. From our syllabus, the main topic what we are dealing with is electricity and measuring instruments, which is 5th chapter in our syllabus. For today's class, from this chapter, we are going to discuss about moving coil galvanometer. Now, to understand this topic, we are using a PowerPoint presentation. We can see photographs also if they are needed. The main objective of today's class is, on completion of this period, you would be able to understand what is construction and working of moving coil galvanometer. Now, before moving on to today's class, let us recall what we discussed in previous class, that is recap for our today's class. In the last period, we studied about meter bridge and its importance. Actually, we have studied superconductivity. So, you can take it as superconductivity. Now, what is moving coil galvanometer? Now, it is a device which is used to measure and detect the small electric currents. To measure small electric currents, we are going to use a device which is known as moving coil galvanometer. Now, as we have seen our chapter as electricity and its measuring instruments. So, it is the instrument to measure electric current. So, we can detect and also we can measure electric current. Now, what is the working principle behind moving coil galvanometer? Moving coil galvanometer works based on the principle that when a current carrying rectangular coil is placed in a magnetic field, it experiences torque. Under the action of this torque, the coil rotates and this deflection in the coil is directly proportional to the current which is flowing through the coil. So let us see what is the construction of moving coil galvanometer. Now here we can see galvanometer consists a rectangular coil PQRS. It is a coil, rectangular coil, which is having n number of turns of insulated copper coil, which is wound over a non-magnetic metallic cylinder. The coil is placed between the poles of the magnet. These magnetic poles are in concave shape. Due to this shape, it produces radial and high intensity magnetic field. Now you can remember this point, why these magnetic poles are in concave shape, because it produces radial magnetic field with high intensity. A non-magnetic metallic cylinder should be filled with a soft iron. Now this soft iron core increases. Why it is filled with iron core? Because it increases the strength of the radial magnetic field due to its high permeability. As iron is having high permeability, because of this it increases the strength of radial magnetic field. The coil is suspended by a phosphor bronze strip through a torsion head. To that, it is free to rotate about the vertical axis. With the help of this, it is free to rotate about the vertical axis. To other end of the coil, it is connected to the light spring and finally to the terminal T2, and the torsion head is connected to terminal T1. Now you will understand it clearly when you look onto the picture. A concave mirror is placed to the suspension strip to note the deflection of the coil using lamp and scale arrangement. Using lamp and scale arrangement, we can measure the deflection of the coil. Now here you can see a beautiful picture which is showing us the of moving coil galvanometer. Here you can see a torsion head phosphorus bronze strip which is connected to torsion head T1, and the other end of the coil is connected to T2 torsion head. Now here you can see N and S, which are poles of a two poles which are in concave shape, and we can see a mirror M which is used to find the deflection of the coil. Now here you can see how a radial magnetic field turns the rectangular coil. So let us move on to the theory of the moving coil galvanometer. Now here we have seen that PQRS be a single turn of the coil and a current I flows through the coil. In a radial magnetic field, the plane of the coil is always parallel to the magnetic field, which is of strength B. As it is parallel to the plane of the coil, the sides QR and SP are always parallel to the field. Now as they are parallel, nothing but they are in the direction of magnetic field, so they don't experience any force. So the other two sides of the rectangular coil, they are PQ and RS. They are always perpendicular to the magnetic field. That is what you can see here. PQ and RS, which are perpendicular to the magnetic field. You can see in the dark lines, they are showing the direction of magnetic field B. So for these lines, these two sides PQ and RS are always perpendicular. Now let the length of the coil, that is PQ and RS, is L, and breadth of the coil, that is PS and QR, is equal to B. Now force on PQ is given by BIL. According to Fleming's left-hand rule, this force is normal to the plane of the coil and acts outwards. That is what you can see here. It is moving outwards. Force. So the same force which acts on the side RS is BIL. Now this force is normal to the plane of the coil and acts inwards. So one force is acting outwards and one force is acting inwards. So these two equal anti-parallel forces produce a torque and they deflect the coil. So the torque produced here is given by force into perpendicular distance between forces. So force is BIL and perpendicular distance between them is B, which is breadth of the rectangular coil. So we got BIL into B, length into breadth, that is area. So if there are n number of turns in the coil, the torque produced is NBIA, where n is number of coils, B is strength of magnetic field, and I is the current which is flowing through the coil, and A is area of cross section. It is not area of cross section, it is area of the rectangular coil. So the rotation of the coil produces a twist in the suspension wire, produces a resisting torque which is directly proportional to the angle of deflection. So at equilibrium, deflection torque is equal to restoring torque. So NBIA is equal to K into theta, where K is the torsional constant of the spring. which is nothing but the restoring torque per unit twist. For one twist, how much it is rotated, that is torsional constant. So by using the equation NBIA is equal to K into theta, we can find that the electric current in the coil is given by I is equals to K by NBA into theta. Now here K is constant, number of coils, nothing but number of turns in the coil are constant, magnetic field is constant, and the area of the coil is also constant. So we can take all the terms which are in the bracket are constant. So therefore we can say that I is directly proportional to theta. So what it says us that the deflection of the galvanometer is directly proportional to the current which is flowing in the rectangular coil. So lamp and scale arrangement by using lamp and scale arrangement, we can find the amount of deflection in the coil which is equal to the amount of current which is flowing in the coil. So what we discussed in today's class, let us summarize. We have discussed the construction and working of moving coil galvanometer. So let us see how much we have learned using some questions here. What is moving coil galvanometer used for? Is it used for measurement of voltage only, measurement of resistance, measurement of small currents, or measurement of electric field? So obviously it is used to measure small currents. Now a moving coil galvanometer carries a current I and the magnetic field B, which is radial. The coil has n number of turns and an effective area A. The torque acting on the coil of a moving coil galvanometer is given by, so we have seen this in the derivation. So that is NBAI. That is C is the correct answer for this question. So the deflection theta is related to the electric current I in a galvanometer by the relation proportional to theta or tan theta, sin theta or cos theta. It is proportional to theta. Simply it is proportional to angle of deflection. So it is A is the correct answer for this question. What is the shape of a magnet in moving coil galvanometer to make the radial magnetic field? So this is also we have seen whether it is convex, horseshoe, concave or none of the above. It is concave. To produce radial magnetic field, we use concave cylindrical magnet. So here are some frequently asked questions. Explain moving coil galvanometer. So with the help of a diagram, we are going to explain what is the construction theory and what is the relation between I and theta in the first question. And in the second question, it is simply to draw a legible sketch of moving coil galvanometer. So with this, we are concluding our class. So what we discussed in today's class, that is about moving coil galvanometer, which is the instrument used to measure electric current. Thank you so much. Let us understand the concept of moving coil galvanometer with the help of a small video here. We'll see the principal, construction and the working of moving coil galvanometer now.
Today we will discuss about the moving coil galvanometer. What is moving coil galvanometer and what are the parts of the moving coil galvanometer? Firstly, we have a base with leveling screws and a frame in which our moving coil galvanometer will work. We have a north pole and a south pole magnet with a rectangular coil inside the north pole and south pole. We have a torsion head on the upper portion of the frame, terminal 1 on the left side and terminal 2 on the right hand side. This torsion head is connected to the rectangular coil, and also this is connected to the terminal 1. Rectangular coil is connected with the elastic spring, and this elastic spring is connected to the terminal 2. There we have a soft iron core in between the rectangular coil for providing radial magnetic flux from the north pole and south pole magnet. So these are the parts of the moving coil galvanometer. Now we will discuss about the working of the moving coil galvanometer. What will happen? There is a mirror for observing the coil rotation. Now north pole and south pole magnet will give magnetic flux which will produce rotation effect in the rectangular coil, and this rectangular coil is attached with the spring which will also rotate to some extent. Then this is connected with the terminal T2 and coil upper portion is connected to the terminal T1. The angle of the coil rotation we will measure how much the angle coil will rotate, and this angle will be proportional to the current flowing in the circuit. So from the angle of the coil rotation we can measure the current flowing in the circuit, and this spring will help to restoring the coil position back. As the coil rotate, it will restore it again and again, and we can measure angle of the coil for measuring the current in the circuit. So this is the moving coil galvanometer. Terminal T2 and terminal T1 will also be connected to the galvanometer for direct reading.
Moving coil galvanometer. Moving coil galvanometer is a device used for measuring the current in a circuit. Principle. Moving coil galvanometer works on the principle that a current carrying coil placed in a magnetic field experiences a torque. Construction. It consists of a rectangular coil of a large number of turns of thin insulated copper wire wound over a light metallic frame. The coil is suspended between the pole pieces of a horseshoe magnet by a fine phosphor-bronze strip from a movable torsion head. The lower end of the coil is connected to a hairspring of phosphor-bronze having only a few turns. The other end of the spring is connected to a binding screw. A soft iron cylinder is placed symmetrically inside the coil. The hemispherical magnetic poles produce a radial magnetic field in which the plane of the coil is parallel to the magnetic field in all its positions. A small plane mirror M attached to the suspension wire is used along with a lamp and a scale arrangement to measure the deflection of the coil. Theory. Let PQRS be a single turn of the coil. A current I flows through the coil. In a radial magnetic field, the plane of the coil is always parallel to the magnetic field. Hence, the sides QR and SP are always parallel to the field. So, they do not experience any force. The sides P, Q and RS are always perpendicular to the field. PQ is equal to RS is equal to L, length of the coil, and PS is equal to QR, that is equal to B, breadth of the coil, force on PQ. for BI into BQ is equal to BIL. According to Fleming's left-hand rule, this force is normal to the plane of the coil and acts outwards. Force on RS, F is equal to BI into RS is equal to BIL. This force is normal to the plane of the coil and acts inwards. These two equal, oppositely directed parallel forces having different lines of action constitute a couple and deflect the coil. If there are n turns in the coil, moment of the deflecting couple is equal to NBIL into B is equal to NBIA. When the coil deflects, the suspension wire is twisted. On account of elasticity, a restoring couple is set up in the wire. This couple is proportional to the twist. If theta is the angular twist, then moment of the restoring couple is equal to C theta, where C is the restoring couple for unit twist. At equilibrium, deflecting couple is equal to restoring couple. NBIA is equal to C theta. I is equal to C divided by NBA into theta. I is equal to K theta, where K is equal to C divided by NBA is the galvanometer constant, that is, I directly proportional to theta. Since the deflection is directly proportional to the current flowing through the coil, the scale is linear and is calibrated to give directly the value of the current.